let's say I've got some graph here. So some function that's represented by this black line. And at some x value c, I can draw a line tangent to the curve at that point. So this is the function value at the point c, and this is the tangent line. Now, what I might want to do is figure out how to, we've talked about how to approximate that, but we might want to somehow relate topics we already know about the change in values. So if I slide over some delta x value, if I increment some delta x, that could be a very small number, and in practice it usually is a fairly small number, then what I get is I get a small change, I get the new function output at that new value, and I can compute the difference between the new function output and the old function output, and I can call that delta y. Because delta x is my change in x, delta y is my change in y. And when we think about it this way, those are usually what are called increments of x and y. So we have this equation here, this point slope equation, y minus f of c equals f prime of c times x minus c. And if you think about this, this is really the output minus the function value, so that's like a change in y, times the derivative, or it equals the derivative at that point times x minus c. So that's really, depending on what x is, you can think of that as some distance away from c. Right? So if I plug in c plus delta x here, this cancels, and what ends up being here is just a delta x. So you can kind of think of this as a delta y delta x, basically. So what we say is if the x value is incremented in x by some delta x length, then we call the increment y as this delta y is just the difference in the function values. All we're doing is we're formalizing this depiction there. Now, where we get the part that involves calculus, because notice none of this involved calculus. Well, that involved calculus a little bit, but this didn't. This piece just said that the change in y is the function output at the new value minus the function at the original value. That's not really anything. That should be a C, by the way. Sorry about that. That should be a C. So anyway, this is really all it's saying, is that's the change that you've gone through. Now, calculus, we have this idea that this dy dx, and we know that dy dx is equal to a number, and that number is a slope. And if you recall from your studies in algebra, when you think about the slope, you think about rise over run, right? There's some ratio of how much you change in y to how much you change in x. And from a derivative standpoint, there's really no difference, because that's what you're really doing here. You're creating a bunch of slopes that are telling you how quickly y is changing relative to how quickly x is changing. If that derivative value is high, that tells me y is changing quickly relative to x. That tells me that I'm increasing quickly, right? That's all that the derivative is really telling me. So what I can do is I can kind of think of dy dx like a fraction. Now, I want to be very clear. Dy dx is not a fraction. It may look like a fraction, but it is not. It represents a function. However, if you think about dy and dx as these sort of differentials, so that's what they're usually called, differentials. If you think of them as actual quantities, then if I say dy dx equals f prime at c, well then I can multiply both sides by dx, which is weird to think about because it's not a fraction. But if it were, the dx would cancel over here, and you'd have a dx on this side. So what you'd have is this. So when we talk about differentials, we're talking about this dy, and we're saying that dy is proportional to dx and the constant of proportionality is the derivative at the point. I don't know if you remember that type of verbiage from your earlier math studies, but when you talk about something being directly proportional to another thing, it was always, A equals K times B, and that K was some sort of scale factor, and that's what this is. Well, so why are we doing this? Well, the reason we're doing this is because what you find is instead of having to do this and calculate two function points, what you can do is you can do this. You can say delta y is approximately f prime at c times delta x. So if you kind of cheat, what you do is you specify that delta x. You say, all right, I want delta x to be small. Maybe I want to be 0.1. Maybe I want to be 0.01 or 0.001. And f prime at c I may have. I may know a bit about f prime at c. Because if I calculate a derivative, I might be able to evaluate that derivative very easily. But I may not be able to evaluate the function very easily. So what I can do is I can approximate how much y is going to change proportionally to how much x is going to change. What this is ultimately telling me is this value of this derivative says, oh, that's going to change quickly at that point, or that's not going to change quickly at that point. And in practice, what this can also do for you is it can inform you about how often you need to take samples. Like for instance, if the value of the derivative is very small at that point, then what that tells me is that the error in the tangent line is going to be very small, because the derivative isn't changing so quickly that it's going to drift away from the tangent line. But if that derivative is very high, then it might be true that you can expect that derivative to fly off. Things you can help with that is if you actually have a second derivative, that's going to give you even more information, but that's beyond the scope of what we really wanted to study right now. So really the big takeaways here are that when you want to compare, when you want to test that, you can take some test points and you can test the function out, the differences here, and get the actual delta y, and then you can approximate it using, and so you know delta x here, you know c, and you can find the derivative at c, right? I'm just trying to give you all the pieces. And then you know what exactly delta y is, and you know what approximately delta y is, based upon what dy is. And then you can compare those and see how they relate. And what you'll find is, in a lot of cases, they're pretty close to each other.